Right. Thank you. Thanks for hopefully paying attention to me. I usually get slotted before lunch or the last session, and I think this time I have this pleasure of being the last session before you all get to go out of here. So hopefully I don't exceed my time, and if you don't ask a lot of questions, we can all get out of here in time. So just going back, my name is Vasanth Waran. I run the automotive business at MIPS. Previous to that, I've had roles running products related to automotive for almost the last 12 to 15 years. I'll be talking a little bit about what we do at MIPS a little bit differently in terms of multi-threading and how it applies to the automotive market. MIPS has been around for a long time. For folks that have not known what we've been doing, in the last couple of years, we've pivoted. We are now RISC-V compliant. But one of the things that sets us apart from potentially a lot of the other players in this market and other competitors with competing ISAs is that we are focused on efficiency. We're focused on data processing and data movement, not particularly setting the alarm bells off when it comes to running benchmarks and so on. And one of the arguments I will make in the next 20 minutes or so is that the automotive market, especially the autonomous market, requires a lot of data processing, and it needs efficient processing that we provide as well. So where we are focused is on markets that, as I mentioned before, require a lot of data processing. And that is applicable, I would say, to the ADAS zonal controller markets in automotive, which is very close to where my heart. But it's also applicable in the data center and the embedded world as well. Won't spend so much time on that today, but more focused on ADAS. And that's where a lot of our solutions today are going in as well. So if you talk to folks that are working in the automotive market, whether it's suppliers such as ourselves, SoC vendors, tier ones or OEMs, right? They typically come up with a couple of pain points in terms of where the market's going and what their pain points are in terms of being affordable and profitable. The last couple of years, there's been, quite a bit of hype. I think now we're starting to see the reality in terms of robotaxis and self-driving cars. But one of the effects that happened was there was a lot of push in terms of performance, right? And some of our friends at ARM had pushed a lot of performance in terms of DMIPS, a spec-int, if you will. And I'll talk about how the TOPS, when it comes to AI performance, is also sort of exploded in the last couple of years, right? And this causes a lot of issues, not just from a die area perspective, but also from a thermal performance perspective as well, right? You can't keep increasing performance and expect the power to be the same, right? And so this is a big problem, and this is where we come in with effective data movement, and we're able to hit the same use cases with much lower thermal requirements. And then from a customer perspective, you're talking to the OEMs, one of the biggest problems they have is how do you keep up with the Teslas of the world or the BYDs of the world, right? I'm not going to get into which car is safe, which car is unsafe, right? But just purely from a technology perspective, these vendors, a couple of these vendors, as well as some of the others in China, they're clearly innovating. They're able to move really fast. They're able to provide new upgraded experiences very nicely, which some of the legacy automakers are struggling with, right? And for that, you have to change the way you design the car. Not in the metal or anything, but just the way software is written and how the ECUs are built. And that is very important in terms of how you address what we call as software-defined vehicle or EE architecture. And then the final one is something that's way out of our hands, or at least mine for sure, is the geopolitical and the supplier independence, right? With each of the regions starting to get very deglobalized, if you will. This is creating pressures in terms of having architectures that are transferable. These OEMs ship across all nations, and they need to have a solution that is fungible to some extent, right? So they're able to take one architecture and then take it to another country or another region. And that's where I think having a RISC-V compliant architecture is really helpful. So you can go implement it in a certain way in one area, and then you can implement another way as long as the ISA is compatible. I think you have a fairly transferable solution. I'll skip this in the interest of time. OK, I want to spend a little bit of time here, and then we'll get into some of the areas that I'll talk about. So when you'll hear this word thrown around when you talk to automotive vendors, EE architecture, fundamentally stands for electrical engineering architecture. It's the rewiring of the car, if you will. Sort of an oxymoron because they're actually trying to reduce the wiring harnesses and the cable weights in the car. And there are many ways to slice and dice this, but if you're looking at cars that are coming out in the next 5 to 10 years, predominantly a lot of them are going to have this form of architecture where they have zonal controllers or zonal gateways, which talk to the sensors. And they will all interface into like a central gateway. The interface on the cars have typically been the slow CAN, linear interfaces in the past. Now they're switching to Ethernet. And they'll connect back into the brain of the car, which would be what I call HPC here, is high-performance compute, which is an IVI, infotainment display, or a ADAS solution. Now, that ADAS could have redundancy built into it, and we'll take a look at that. So these are the main building blocks of this architecture. Each of them have very different performance needs, right? The zonal gateways, these are MCUs that are talking to sensors or IOs. They don't really need a lot of performance. They need a lot of real-time performance, right? So they're real-time heavy, but from a performance perspective, they're probably in the low to the mid-range. They need to be absolutely safe. So when you press the brake, it needs to stop. Or the self-driving cars, the actuation needs to happen correctly. AI is low. You could argue with me that there's more edge AI coming in, but today the requirements on the AI side is low. And then if you look at the sensors, very similar to the zonal gateways as well. A lot of real-time performance, very heavy on safety. AI is low. Where it starts to get at least a little bit interesting in my world is on the gateway and the HPC side, where there's a lot more performance coming in. On the gateway, you still need to be pretty heavy on the real-time performance. Performance is starting to go up. What used to be traditional CAN microcontrollers is now becoming more of MPUs. And then there's more AI that's seeping in there as well. And then finally, when you look at the HPC, this is where our friends at NVIDIA, Qualcomm, Tesla with their FSD, this is the chip that they are bringing to the market every year or every other year. Performance has gone through the roof. We'll take a look at that in the next couple of slides. Now, they do have some real-time performance because they sort of loop back into some of the other controllers that we talked about. And here, the AI performance needs are, it's not even going up 2x. It's probably going up like 5 to 10x every year. So when you look at the performance levels, and at the bottom, you see these L2 to L5. These are the SAE, Society of Automotive Engineers, levels that are needed for ADAS. And I've called out two metrics. I don't want to have an argument about whether DMIPS is the right one or not. This is what we get from customers. We go hoarse shouting with them about DMIPS being a bad metric. But just for the sake of discussion, right? If you look at the way things scale, you almost see CPU performance double as you go from L2 all the way up to L5. Now, some of that is because of redundancy. As you go up in terms of safety levels, you do need to have fail-safe methods so that you have a second system coming in. But a lot of it is also because of the configurations that you will see in the next few slides. Now, similarly, on the top side, AI benchmarks, if you will, at the low end, it's fundamentally camera-focused. Today, a lot of the cars that have self-assist or driving assist have L2 systems, front-facing camera systems that are vision-based. But as you start to go up the curve, you bring in more sensors, higher resolution, needs to react much faster as well. And that's where the AI capability starts to explode as well. So you can see it goes from about, I'm going to say about 50 tops all the way up to about 2,000 tops at the top end, right? It's almost a 40x increase. The problem for all of us is you have to design a system that's scalable, affordable, at the same time needs to be thermally viable as well. And this is just a view of what a typical system would look like, right? So I took an L3 view, right? An L3 car. You can make an argument that this is not a prescriptive solution. There are many ways to skin the cat, if you will. This is one of them. You can see the different sensors in the system. The resolution of the cameras have gone up quite significantly. The last time I was working on one of the RFIs, I saw a 17-megapixel camera coming in. So, and then the field of view was also much wider as well. Frame rates go up. So in aggregate, what you see is data rates up to 50 gigabits per second, even going up to 100 gigabits per second. And this is probably going to double in the next two years, right? Cameras, as I said, are getting cheaper. Sensors are getting cheaper. More and more radar is getting added. In some cases, there's more redundancy coming in just from a safety perspective. That's a lot of data to move. It's not a DMIPS problem. It's not a TOPS problem. It's a data movement problem. And I won't spend time on it, but you can typically see what sort of workloads do we see on a CPU, for example, right? A lot of camera processing, a lot of radar processing, LiDAR, sensor fusion. Everything sort of gets dumped into CPUs as well in terms of miscellaneous handling. And some of this is just legacy. If there are any software engineers here, just shut your ears. Poor code that's been written over years. But it's sort of filtered into the systems that we have today. But you can see, even though you might have dedicated accelerators, the CPU is still being relied on for quite a bit of offloading. So what do SoC vendors do today, right? So what we see in the market is one of two. You have a brute force approach where you put a lot of big cores, right? In this case, I've shown our friends in Cambridge their A cores and their R cores, right? Typically, you need some safety, which comes from the R cores. The A cores is where a lot of the offloading happens. And the niceness to this is that you have control and compute on the same A cores. The R cores will typically run some sort of RTOS or safe OS. It's easier programming, right? And this is one of the reasons why some of the big SoC vendors that are winning because their software story is much better than the others. But the problem with this is you sort of dedicate big cores to do peripheral I/O loads that we saw in the previous slide, right, in terms of all the sensors coming in. So it's a very ineffective solution. You're taking a big hammer to hit a very, very small nail, right? It's not the ideal approach. And then just in terms of the traffic, there are frequent context switches. You have steal cycles coming in from the compute subsystem, cache thrashing, et cetera, right? And the biggest problem in a lot of these systems, anytime we architect one of these systems, we always run out of memory bandwidth. As I said before, our friends in the software world, they find applications to run and kill all the memory that we have on the system. And just this architecture itself lends itself to a position where the memory bandwidth is trashed very easily. Now, what we see on the other side is what I call spread the wealth, right? You have a mix and match of different CPU cores. You can have big A cores sprinkled with a lot of smaller A cores or smaller R cores, and then you have the safety R cores as well. So the safety cores perform the same function. Rest of the architecture is similar. What this does is it's more efficient because now you've sort of taken the small cores to partition that for some of the peripheral loads or the sensor processing loads, right? And in some cases, they have better real-time performance if you're using an R core, for example. So it does function better than the other scenario. The problem, though, is on the software side, right? Now you have a lot of mailboxes that have to be taken care of. The architecture is different between the different cores. It's not monolithic. And the software burden becomes extremely hard. And as we all know, the car is becoming more and more software-driven rather than hardware-driven. And that's one of the reasons why some of the traditional SoC suppliers that had that sort of architecture have sort of have been out of fashion compared to the newer ones that are coming in. So this is just another view of how the system looks from an SoC perspective, right? You have all these sensors connected. That comes back into the HPC, the high-performance SoC. In this case, we were just showing some of the camera groupings. You get thousands of interrupts per second, lots of context switching, cache thrashing. So running a synthetic benchmark, we are all forced to do it. And I'm not going to lie, I do it as well as anybody that I'm competing with. We all have to supply these benchmarks. But they don't really reflect what happens on an ADAS system, right? And that's where we come in, right? So this is an example of one of the products that we're building, right? So we have what we call as SMT, Simultaneous Multithreading. And the advantage here is that you can run multiple threads at the same time, right? Not rocket science. But the fundamental thing is you can have some cores dedicated to, or some threads dedicated to I/O processing while the others are processing something else. When you have interrupts, you could prioritize, get the task done faster, more efficiently, not just in terms of performance or frequency, right? Much more effective in terms of how you can address an ADAS problem. This is one of the reasons why MIPS has been a leader in this area. We've been shipping solutions in the automotive market for a long time. It's built on some of the legacy that we have from our old MIPS architecture as well. So how do we do it? I'll talk about the one on the left and on the right. It's just the scaling that we have in terms of the different clusters and the cores that we can do. Very similar architecture, right? But what we have here is our performance cores along with our real-time cores. Similar architecture, so you have control and compute on the same sort of cores. Ease of programming. We have multi-threading, so what it does is you get the highest performance, as we talked about. In terms of data movement, you get about 20 to 30% efficiency, better efficiency for interrupt-heavy sensor fusion applications, which is exactly what ADAS is, right? A lot of sensors coming in, needs to be fused, needs to be stitched, sent to an AI engine, and then then you do a control decision based on what the AI engine tells you. And the other one, big thing that I think a few of the speakers ahead of me talked about was safety requirements. The real-time cores would give you that safety requirement that you need in terms of providing higher ASIL levels. And then, of course, given that you're not pushing DMIPS or spec-int, right, you're not pushing the envelope in terms of frequency and more cores. So you have lesser area, so lesser cost in terms of cooling as well. So a lot of secondary benefits in terms of adapting this sort of architecture compared to what we see in the market today. I think the right side just shows you what we can do in terms of cores to clusters to the number of threads we can run simultaneously. So where are we going with this, right? Now, if you take a car, so the one on the left is the HPC, the high-performance compute, with a lot of the sensors coming in. So you need a lot of data movement. You need to do sensor fusion, which this is where we're pushing our multi-threading, right? So you have a low-latency solution for that. And it can also become the backbone for GPU compute or any sort of AI accelerators that come in as well. And on the right side, we didn't talk about this today because I focused on the HPC. But when you're talking about low-latency, real-time performance needs, that's also an area where the multi-threading helps. And you can get up to about 2x cycle reduction when you go into those applications. So it's not just applicable at the central compute. It's also applicable at the zones. And so this goes back to the original slide I had in terms of how do you architect the car to solve this SDV problem that we have. Very quickly, we'll talk about how to scale, right? So we saw L2 going all the way up to L5. This is a slide. I think I stole this picture from somewhere. So the fundamental message we're saying is that the performance is now going way beyond where Moore's law can scale. And then now the other problem that you see is I think there was a public notice from TSMC in terms of the wafer prices, right? Those are not keeping up with the new technologies that are coming in. So just because you're jumping a tech node, it doesn't mean you're going to get economies of scale. So the laws of physics are starting to be bent, if not broken. And so just throwing more and more gates at it is not going to be the solution, right? So that's where chiplets comes in. And we are also looking at building chiplets, going into solutions that provide CPU or hardware accelerators that go into chiplet solutions, right? So how do you do it? You could do a core from us, build clusters, and then those clusters can go into chiplets, right? So this allows you to scale if you have to have the higher performance, if you want to have the redundancy. It's another way where you can address this problem. I think this is my last slide. Again, just to sort of bring everything back together, in terms of efficiency, I don't think there's any better solution in the market in terms of addressing it than what I've seen here before, what I've presented to you today. And we're also able to provide the scale that you need to go from just a L2 solution all the way up to L5 solution. And then primarily, we're able to do it because we're focused on the end market. For automotive, we're designing these the cores to provide the acceleration that's needed for sensor fusion or zonal controllers as well. And that was it.
Thank you. How many hardware threads do you typically implement per one of your MIPS processor cores?
It's going to vary. It depends on the core you're using, right? Some have 2, some have 4. So it's going to vary depending on the cores that you use.
Are there any other architectural changes you've made to the ISA to support your particular multi-threading?
Not to the multi-thread. We do some other. We do have some secret sauce that I can't talk about, but we do have some secret sauce that we implement as well.
Just a curiosity, in the high-performance computing, AMD, Intel, they seem to have dropped, especially Intel, the hyper-threading technology. Probably one of the reasons is that the cache locality then gets much worse, and latency can increase for the single thread. Do you see these problems what is different in the automotive sector?
Well, it's a good question because I started my career at Intel as well. And we used to do, obviously, multi-threading and hyper-threading all came out of x86 way back, right? I think automotive in general sort of moved away from it. I'm going to say probably the mid-2010s. There's still arguments, even within MIPS, we have arguments on more cores or more threads, right? I think it's the way you implement it, right? You have to have proper software support. You have to have proper scheduler support, et cetera, to extract the maximum value out of multi-threading as well. Pros and cons to each of them, but now I think it's gotten to a point where people are putting so many cores that it's just getting inefficient, right? I think now you'll start to see the shift towards multi-threading, in my opinion. Okay, thank you. You're all free to go.